First, let's start today's seminar. Today, we are very happy to have Professor Yang Bai from University of Wisconsin-Madison to talk about QCD-Collapsed domain wars. Please start.
Okay, thanks for the invitation. So today I will talk about QCD-collapsed domain wars and also related stuff. I will first give you some motivation for why we're doing this project, and so get to the next slide. Still need this way. Okay. Okay, so the main motivation still it's about dark matter. In instance, what is the 27% of the total energy of our universe and how to understand that. So that's pretty much the motivation for me to trying to understand. And when we think about dark matter, then sometimes we can see that there are many possible models. And here, just to give you a little bit of incomplete list of dark matter models. As you can see that it spans from like a quasi dark matter, which is dark matter mass like 10 to 22 eV, which is matched to the galaxy size, and versus like sometimes we talk about a primordial black hole, which can have a dark matter mass to be solar mass. As you can see that the range could be like a 88 orders of magnitude. And in the last few years, I was mainly working on the, sometimes we can call it like a microscopic dark matter. In a sense, the dark matter mass is above like a Planck mass, so which means the dark matter is some composite dark matter model. But also there are lots of activities, especially for the axion dark matter models in the literature. And okay, so but if I come back to the first this kind of a slide, right, about the energy pile of the universe, one interesting question you can ask that all those percentages, they are kind of robust. You can ask the ratio of the dark matter over ordinary matter. So in instance, that ratio will be 26.5% over 5%, which is around 5%, for example, right? So the obvious question one can ask is why the dark matter energy density is comparable to the ordinary matter, right? So why is that? So naively, you think about this question, you maybe say, oh, I don't care that much because that's just some order one number. And sometimes we do see like routine life, there are many object sizes, they are comparable to each other, right? Like a human being versus the table size, for example. So they are, example, the ratio of those length, they are order one. But however, that's not the case for this factor of 5. The reason is because of the denominator, which is a 5%. There is a little bit more story about that. Instead of the denominator, we say, oh, that's the ordinary matter. But ordinary matter has only baryon, mainly baryon, no antibaryon, right? So we also know that if in the early universe, you have baryon, both baryon and antibaryon in the early universe. So they are both populated from thermoplasma. Later on, after baryon antibaryon annihilation, so you're left with the later baryon, which is take the ratio will be number of baryon minus the antibaryon. That's like a 10 to minus 10 level. So in order to understand this baryon antibaryon symmetry, and one can kind of naively go through the cycle of 3 general conditions to understand that, right? So trying to understand, for example, you may need a baryon number violation, you may need a C and a CP violation, you may need a departure from thermal equilibrium. And there are many models trying to understand the baryon antibaryon symmetry, like electroweak baryogenesis, leptogenesis, and so on. So now you come back to that factor of 5. You ask why the dark matter is comparable to the leftover of baryon symmetry. So that becomes kind of an interesting question now, right? So you think about it. So the ordinary baryon, this 5% in the denominator, has a very long trivial story, like several ingredients from Sakharov's condition. And for some reason, the dark matter is comparable to that leftover, which is a factor of 5. So like even in the literature, there are some people say, one maybe thinking about explaining this factor 5 using like a symmetric dark matter model. And usually people will think about the energy density of dark matter is mass times the number density. The ordinary baryon is, let's say, proton mass times the number of proton energy number density. So like even you could say, I need just two conditions to explain this factor 5. For example, you could have like comparable number density for the dark matter versus the number of density for the baryon. And the second condition, if that is satisfied, the second condition you need to have is dark matter mass is comparable to the baryon or proton mass, right? To have this product of the ratio of the products to be comparable to be 5, right? For the first condition, there are lots of studies for the first condition, and many people are thinking about how to explain the number density of the dark matter is comparable to the ordinary baryon, right? So, but for the second condition, it's a little bit trickier. Because after you satisfy the first condition, you ask, now we will also need to explain the dark matter mass comparable to proton mass, right? But you can ask where is the proton mass comes from. We know that 90% of the proton mass coming from the QCD. So here I just show like from PDG, just give you an idea. Everybody knows this plot, right? So which is the gauge coupling, QCD coupling as a function of the renormalization scale. And we know that when we go to the lower end, below like a GeV or 100 MeV, the QCD is confining, and the proton mass is coming from the, in some sense, strong confining force among quarks, right? And so now you ask, if we follow this kind of logic, trying to explain the coincidence problem of dark matter energy density with ordinary matter energy density, and we ended up with this condition 2, which is proton mass for some reason is comparable to dark matter mass. Then for some reason you get a conclusion like dark matter for some reason needs to know the QCD scale. That's kind of a very simple, maybe very simple-minded way to think about this question, right? But this just to some extent is one of the logical-wise possibility that we need to think about how the dark matter physics or the explanation for the dark matter, how that is tied together with our QCD sector. So that's kind of the one of the main driving question, which is which I keep thinking about this kind of a question. And I think around 10 years ago, and I thought about a possibility one, which is a little bit how do I say, like just to think about beyond standard model physics. We introduce additional, maybe similar. There is a dark QCD, and maybe the dark matter is dark baryon from the new QCD, like strong dynamics in the dark sector, for example, right? So that's very simple mind, and trying to use what we learned from the ordinary QCD sector, and then we say, maybe for some reason now we want to explain the dark baryon mass is comparable to ordinary baryon mass or ordinary proton mass. Then this becomes a question to explain the dark QCD confinement scale is comparable to ordinary QCD confinement scale, if you just follow this flow of logic, right? So one thing we already know, right, from the gauge coupling running, right? So if I throw another like a dark QCD, I have no idea what is the quote-unquote confinement scale. If through a dice, and the confinement scale of the dark QCD could end up with a different scale, right? So that means that unless there's some reason the dark QCD and the our QCD, for some reason they're kind of gauge coupling related to each other, such that they are know each other till IR scale, for example, and maybe that can be a way to explain why their confinement scale are comparable to each other, right? And, so that's kind of the underlying logic, but indeed there is some way to arrange that, which is using the so-called infrared fixed point idea, for example, right? In essence, you say, I just think about there are two independent gauge coupling, one for our QCD, let's call it alpha S, and one for dark QCD, call it alpha D. Maybe I can think about this in general, right? So there are some bunch of fermions and number of fermions charged under our QCD, call it NFC. Number of scalar charged under our QCD, call it NSC. Number of fermions under dark QCD, and similarly for this notation, right? And also some fermions maybe charged under both joint, right? And instance, for example, bifundamental under our QCD and the dark QCD, for example, such that they can couple the gauge coupling for those two sectors together. And then you maybe have a chance for some models, you could have both gauge couplings reach to beta function to 0, such that their gauge coupling is not running, or instance reach to some infinite fixed point. So here I've just used some toy example. Actually, it's not really toy. This can be implemented with certain choices of matter content. You can start with some UV scale, different gauge couplings for those two gauge group, and let it flow in the IR, and the gauge coupling potentially could reach to some kind of fixed point such that the final gauge coupling in the IR is insensitive to the UV boundary condition of the gauge coupling, right? So that's the meaning of infinite fixed point. So now you can see that suppose there are some fields, for example, is charged under both QCD and dark QCD, and suppose they decouple at some scale capital M. Suppose the capital M is not too far away from the QCD scale, then the dark QCD and the our QCD gauge coupling, they run independently. Then you have a chance their confinement scale may be comparable because they kind of only starts to run at deviate from each other or unrelated to each other at some decoupling scale capital M, for example. Right? So we need to try to just exhaust some kind of matter content, different number of fermions, scalar, and so on, and also some fermions and scalar charged under both QCD and dark QCD, and choose some kind of decoupling scale capital M. And as you can see that generically, we could identify a bunch of possible models, the infinite fixed points, and with some decoupling scale like a TeV scale or 10 TeV scale, and then potentially we can have the MD. MD, you can think about it as dark baryon mass, which could be a dark matter candidate, and the dark baryon mass would be like a 10th of GeV. As a result, you could use this kind of infinite fixed points way to have a dark baryon to be related to the R baryon mass, for example, right? And obviously, this is just try to explain the condition 2, right? But we still need a condition 1, which is the ratio of the ordinary the dark matter lumbar density is comparable to ordinary baryon lumbar density. That is there because I already listed many activity along that direction, right? So you can also use some kind of leptogenesis like this dark baryon over ordinary baryon mass ratio. Then you potentially can explain this factor of 5, and some models you can accommodate this factor of 5 in the so kind of we work on that 10 years ago, and also there are some interesting phenomenology along this direction, including some kind of emergent jets and some Large Hadron Collider experimentally assertion for that, for example. But also we can ask come back, right? So we can ask ourselves, is like do we need a little bit of complicated dark QCD sector with so many fermions, scalars, and or we are just doing too arbitrary thing, right? So we just introduced too many unknown degrees of freedom. So even though the idea maybe it's correct, right? So that's kind of we kind of drives us to think about some simpler possibility, right? But before I talk about a simpler possibility, any questions so far? Anybody has any question? You can stop me at any time. So, Minho, do you have a question?
No, I don't have one. Sorry.
Okay.
I understand.
Okay. So now, if there is no more question, then let me continue with maybe some simpler possibility. Okay, simpler possibility is can we entertain the possibility to have a maybe to have a dark matter from our QCD, right? Basically, we kind of give a little bit of simple logic. Maybe dark matter hiddenly knows the QCD scale. So then, obviously, you ask, what is the chance we can explain dark matter within our QCD, right? And to tell you the truth, that's pretty much what is my main kind of interest at this moment for there are still several projects trying to explore on this direction. So now come back to our QCD. So what we're plotting here from other reference here, which is the temperature versus the chemical potential. You can think about the chemical potential, roughly speaking, is the Lambert density of a barrier number density. Normal situation, we have normal like a vacuum. So the chemical potential is very tiny and 10 to minus 10 level, for example. So you have the QCD phase transition is like a crossover in the but when you have the barrier number density very high density region, for example, inside a neutron star, you could have some other possible states of the QCD. For example, people talk about like even color superconductor and some other organic matter and all kinds of interesting possible phase inside QCD. Okay, so but today I want to talk about one possible states, which is the so-called quark nuggets. Just in case you are not very familiar with this object, to the zeroth order, you can think about this object is very similar to white dwarfs or neutron star. For example, white dwarf is the stability in some sense is a balance between the like electron degenerate Fermi pressure balanced by gravitational pressure. And but when we think about the quark nuggets, which is a little bit small object, so gravitational force does not play a role. But you do have the situation, have the so-called vacuum pressure. So what is vacuum pressure? So in outside of this quark nugget, we have the normal QCD vacuum, which means we have a confinement, we have a chiral symmetry breaking, and we have a free state to be like a neutron and a proton, right? So that's our normal hadron states. But inside of this quark nuggets, the QCD is unconfined. The chiral symmetry is not broken. And then inside you basically have a quark gluon plasma basically. And except that you are working in zero temperature, there is so basically you just have some degenerate Fermi dice for those quarks. And so those degenerate Fermi, they provide a pressure. And we also know that inside is not in the quote-unquote the vacuum, the global minimal state. So that's why there is a vacuum pressure trying to push trying to occupy this unconfined phase, right? And then you can reach to a balance between degenerate Fermi pressure and the vacuum pressure. And that balance will determine this, you think about you fix some baryon number for this object. And that balance will tell you the mass over baryon number, which here we just use atomic mass number. And with some kind of parameter, which is a parameter called capital B, is trying to match the vacuum pressure difference in some sense related to the vacuum energy between confined phase and unconfined phase. So, so this one you can do some simple degenerate Fermi calculation, take into account degrees of freedom, and roughly speaking, it's 5.7 times this bag parameter 1/4 power. And if you put some value, reasonable value, which is still a lot of uncertainties about this value, say QCD scale 160 MeV, then you will get the mass over baryon number or atomic mass number to be 900 around 10 MeV-ish. And you realize that there is a chance for this quark nugget states to be even lighter in terms of mass per baryon, lighter than iron. And we know that from periodic table, iron is the most kind of a stable element, right? And if you have some other element, which in some sense you kind of think about some very heavy atomic mass number or extremely heavy elements in the periodic table. And the mass over baryon is even lighter than iron. And so that means that this state, if you produce, this will be even more stable than iron. Right? So that means that this state can easily survive if it can be formed and in some way, right? Okay, so in some sense, that is one, probably in my opinion, one possibility maybe QCD can give us. And then you can ask the next question is, how do you form those states? Right? And the formation of these states has been worked out to some extent, emphasized or worked out a long time ago by Witten. And anybody has a question? Okay, no. Okay, let me continue. So which is the formation of those type of objects from a first order phase transition, for example. So what's the idea? The idea is you start with high temperature first. You have basically quark, gluon, and plasma. And so this is a high temperature phase. And you cool down. And at some point, if you have a first order phase transition, then you have some bubbles coming from the volume. And those bubbles, some bubbles, they were trying to expand. And when they expand, they will push those quarks. And some quarks will enter the bubble, the low energy phase, which is the confining phase, for example. And but some quarks, they will decide whether they want to enter inside the bubble or they want to stay outside. And obviously, you can check the energetically whether they gain mass inside. If they become heavier. Suppose you put the 3 quarks together. If they become heavier inside the bubble versus outside, then probably they will be bounced back by the bubble wall. And then as a result, you will have a little bit fewer number of quarks or baryon numbers inside of the bubbles, and more quarks or baryon numbers outside of the quarks. So for example, you will squeeze a bunch of quarks in a small kind of a high temperature phase, which is a red color, and the low temperature phase will also have a little bit smaller number of baryons, maybe. As those bubbles expand more, and at some point you maybe occupy half of the volume, and then you can think about the environment is low energy phase, and so which is a blue color, and then you have a little bit of pocket of space, which is still in the high temperature phase, and then there are some quarks inside that high temperature phase. And now you can see that if you continue the low energy phase squeeze that pocket, and at some point the quark degenerate Fermi pressure will set in and to hold that low energy phase expansion, and then you potentially can form those quark-Laggett states. Okay, if we think about there is this kind of a formation story, and you can naively use what is the one hep-ph, what is the total baryon number, and divided by how many bubbles or how many pockets within that hep-ph, and that will give us an estimation what is the generic baryon numbers inside one typical quark-Laggett, for example. By doing that, you can estimate get some large number. Then we can get the averaged quark-Laggett mass. And so from that very naive estimation, you can basically get the mass of the quark-Laggett is around 10 to 14 gram, which is a similar mass like some large a craft carrier. But also because the quark-Laggett is almost like a nuclear matter, and the energy density is just QCD scale, right? So it's just nuclear energy density, and the radius is tiny, is like 1 centimeter if we use this benchmark number, and you can almost think about this like a micro neutron star, and except that the gravitational force does not play a role. So this will be one example for microscopic dark matter, and but obviously if this is the end of the story, that means that we should probably most of our physicists or particular people interested in dark matter should work on this kind of quark-Laggets. And but then we say, oh, why we don't have so many people working on this? And there is obviously there is a reason. because
Question.
yes.
So I think the mass of the Cook nugget in general depends on the symmetry of baryon number, right?
Depends on the baryon number, actually. Yes.
So in the top of this slide, so
yes.
I think you have used the observed value of symmetry, right? Is that correct?
Oh, I see what I mean. You're correct for this slide. Yes. So yes. So we did use around 10 to minus 10 for the baryon anti-baryon symmetry multiplied by the total that give us the total baryon number inside one hep-ph. Yeah, we did use that to estimate this 10 to 14 gram. So I didn't go through the detail because there are still a lot of uncertainty. If you do have a first order phase transition, you also need the counting of the number of bubbles. Is there still like a wide range of uncertainty? So yes, you're right. Yeah.
Thank you. And I have one more question. So is it possible to realize the first order phase transition in realistic QCD? So I think the order depends on the number of flavor or number of quarks.
Yeah, actually very good point. So yeah, actually there is one more slide which maybe I can go through more ideas, and actually which is one of the part of the motivation for this talk, and I will get into that. Thank you.
Okay.
Yeah, as what
sorry.
Yes, go ahead.
Because now I can ask question. So this Quark nugget is something always happens in QCD phase transition if it's a first order. Inevitably happens all the time.
Okay. According to the picture, for example, according to earlier time, like Wheaton or also some other Hogan and the company, so they did estimated the formation, and they do get a positive answer for this question. Later on, there are some studies, and people one of the leading question, which is the following: even you after you form those quark nuggets, right? For example, so you maybe also need to keep tracking how the quark nugget evolve, because you still maybe have a proton, you maybe still have a antiproton. So if your antiproton meet your quark nugget, you reduce the baryon number, right? So there is still like a kind of like a BBN, like a nuclear synthesis type of like a reaction chain. In principle, one could keep tracking that. And I think, yeah, last year we also work on some like a solid synthesis, which is similar to this. We also get some kind of conclusion, but it depends on the parameter space for this to survive after those chain of the reactions. So that's one thing. Another thing I also want to mention is when you have the quark nugget, for example, right? So some big size object. So then there is another thing people mentioned in the literature, which is you maybe have the low energy phase popping out from inside of the quark nuggets. So you pop out, then that maybe grow and maybe trying to diminish. But that one also has a little bit uncertainty, and there is no consensus in the literature about that part. So I don't know. I cannot keep tracking the time, but when there is one period of time, probably 80s and then mid of 90s, people before the 90s, people found like confirmed the QCD is a crossover, and people kind of went through lots of papers on that detailed property for the quark nuggets calculation, right? And so in general, yes, it can survive in the current universe. Okay, let me come back to this. Yes, you're welcome. Let me come back to the QCD lattice calculation, right? So I think that's probably like a 2004. So, and also not just one group, but also there is another group from Columbia lattice group, for example, as well. And so they kind of get the QCD if in the small chemical potential, which is normal, like universe history, which is this kind of yellowish, yellow-greenish line, and then you have the QCD phase transition is a crossover, right? But I think the logic, like what I kind of make the motivation for this talk is for some hidden reason, and it's easy to think about that for some reason the dark matter care about QCD. So, but QCD does not give us the complete possibility to form those interesting states to be a dark matter candidate, right? So then this still suggests that maybe we can think of a different way. Instead of introduce a new particle to be dark matter candidate, maybe we can think about like a modify QCD in some way, maybe early universe, for example, and then maybe make the QCD first order, right? And then maybe we can form those quark nuggets, and that be more maybe interesting dark matter candidate because they are made of the same constituents as proton and neutron made of, right? So along that direction, and there are some activity trying to think about how to make a QCD first order. And one possibility is which actually the question, exactly the idea was mentioned previously, right? To raise question, one of the previous questions. So which is like, oh, maybe we can think about it, maybe build some kind of flavor model, maybe the strange quark or some flavon, maybe some Fogg-Lesson way. Make the strange quark lighter during the QCD phase transition temperature, and some kind of delay the strange quark mass below the QCD phase transition, right? And I think with some collaborators, we checked this possibility before, and we indeed find that, yeah, you can write down the model, but if we take the fine tuning into consideration, especially the flavor constraints, right? So you're doing something abnormal, non-trivial in the flavor. So we do find that the model we get is a little bit fine-tuned and which is not very satisfactory. And another idea which you mentioned in the literature, sometimes people say, oh, maybe you add the Higgs boson couples to another like a flighter direction, then there is maybe a combined phase transition such that you can delay the electroweak phase transition. You maybe your potential is flat enough such that you maybe have a supercooling effect, and then you can get the electroweak phase transition even below the QCD scale. But again, that requires some kind of non-trivial arrangement in terms of this flatness of potential, because you can say that electroweak scale is at least three orders magnitude higher than QCD scale. To make that flat enough, that's a little bit of change. So another idea also in the third possibility mentioned in the literature, which is people can arrange to have large lepton number chemical potential, and that can potentially feed back into the barrier number chemical potential. And but later on, people check the BBN and the CMB constraint, found that option is not also not comparable. And so today, yes.
It was echo.
Okay, echo. Okay. So let me, in this talk, I kind of motivated by that, and also trying to think about how to make our QCD first order. And to some extent, maybe there is a little bit easier way to make it happen. So that's pretty much what I want to talk about. So one thing about another way to think about a different phase diagram, which is instead of the temperature versus chemical potential, we can think about the third direction, which is the temperature versus the theta angle. So let's leave aside the theta angle, the strong CP problem, right? Aside a little bit. And there is some, here we just provide some kind of a suggestive phase diagram in terms of temperature versus theta angle. So normally we know that because of the neutron EDM, we know that theta is very close to 0. And we have QCD, for example, to be crossover. But when theta is equals to pi, and there is some suggestive the QCD final temperature phase transition could be first order. And okay, so now I first give you a little bit of support for this phase diagram. After that, I will trying to provide what type of early universe or what kind of a framework or physics model we can potentially have some early universe such that theta equals to pi will be relevant, right? Because if throughout the early universe we have theta equals to 0, there is nothing to talk about, right? And you don't even care about that theta equals to pi is the first order, for example. So let me first give a little bit of support for this phase diagram. And The first support is QCD is over normal at theta equals to pi. So there are a lot of studies at theta equals to pi, which is a little bit more more robust. And the earlier time by Daishin using current algebra, and later on by Witten in the large NC, and more recently by those 4 authors trying to use generalized symmetry, for example. Basically the thing is like in the RGNC, suppose we use Witten's argument, and in the RGNC, then you can realize that the effective potential is NC squared, and just from the simple counting of the gluon degrees of freedom. And then you also need the periodicity, and as well as the continuity of the vacuum energy, and you can get the following possibility, which is the effective potential in terms of theta angle will be a multi-branched function. So what does it mean? That suppose we have NC equals to 3, and you just take a minimum of some cosine function, and 2 pi k is some branching number, k equals to 0, so that's just cosine theta over NC, and which will be which will be for example, will be this green, which will be cosine, sorry, k equals to 0, that will be theta equals to NC, so we should theta equals to 0 should be 1. Yeah, we don't have one. Okay, but you can see that when theta equals to pi, there is a special point. So from this kind of take a minimum of various of branches, then you will get that little bit of cusp behavior around the theta equals to pi. And so that tells you that if you just along the theta direction, you should have a you should have, for example, you should have the first order phase transition, for example, around the theta around the theta equals to pi. And more recently, people use generalized symmetry is trying to say, oh, there's some center symmetry and versus the CP symmetry, because theta equals to pi, CP is still conserving, and they can study the mixed Tofto anomaly about that, and trying to derive that the IR either IR symmetry will be preferred to have like a spontaneous CP violation, also kind of justify that there is some non-trivial about theta equals to pi. But for us, we have another support, which is we could use some kind of little bit simple-minded phenomenologic linear sigma model, and addressed by some like a constituent quark model. Then you can use a 5, which is bifundamental under SU3 or U3 left times U3 right symmetry, and then you have you can parameterize in terms of some sigma field as well as pion field, including eta prime. For example, then there are also some determinant of this bifundamental or the linear sigma model 5 field. Determinant of that will be coupled to the theta angle, and for different theta, for example, theta equals to 0, then we could have the phase transition as a function of temperature, or the vacuum expression value of sigma x, sigma field, and sigma y, which is the CP even field. They will develop a non-zero vacuum expression value, and then you can see that they just have some kind of a smooth changing around some 150 MeV, which is around the QCD phase transition. But for theta equals to pi, as you can see on the right panel, when you around like let's say this specific 129 MeV range, at some point at a high temperature, you have the sigma y, which is the CP even particles, gets non-zero expression value and a small amount of sigma x. But once you below here, you can see that the I, which is a CP odd scalar particle, also get a non-zero expression value. So which tells you that you have a little bit of spontaneous CP violation. And also you have a very, very sharp, and which hints like this is first order. So I think a two combination of that, and that's the reason we think that there is a possibility around the theta direction, the finite temperature phase transition could be first order around the theta x to pi. Okay, obviously there still require a little bit more kind of non-perturbative calculation or proof in the finite temperature phase transition of this phase diagram. That is also a little bit troublesome because yeah, the theta is like a complex number, right? So the lattice also suffers from the sign problem. So it's also a little bit challenging to do lattice simulation or along the theta direction. But maybe there are some other ideas to get a more robust phase diagram of the temperature versus theta for our QCD. Okay, after saying that, now let's think about suppose we first accept that phase diagram, and which I think there is a higher chance that it be correct. Now we think about how to we utilize that to make some changes some Earth universe. Right? So we can think about suppose the Earth universe for some reason there is different patch of the sky of the universe, and some region, some domains which is theta equal to 0, some domains to be theta equal to pi. Then maybe if those domains they happen to survive below the QCD phase transition, so they could have some situation like theta equal to 0, that's crossover, but theta equal to pi, that could be first order, right? And now the question is how we arrange this those different domains, right? And, so now you can see that from the title of the talk, and we maybe can think about the domain walls, right? So for think about the domains, the domain walls, you can think about in general there's some general domain walls, right? So spontaneous breaking of Z2 symmetry, for example. Then you have a solution, classical solution to the equation for motion, and you have this kind of field profile interpolate from like a negative wave to positive wave, right? So then by doing that, then there is a wall and to separate two regions of positive F and negative F, right? And then the wall has a tension. You can use the trace zeros component of trace energy momentum tensor to have the wall tension, which is related to the symmetry breaking scale F cubic. Some order of a number depends on the potential. Right? So the wall tension is the sigma, which is mass dimension 3. Right? Okay, so that's a very standard discrete symmetry domain wall. But we need something special. We need something special, which is we need a QCD anomalous discrete symmetry. So what does that mean? So that means that we need some discrete symmetry, whatever Z2, Zn symmetry, which is anomalous under QCD, such that QCD dynamics will play some non-trivial role on those discrete symmetry, such that if you do have a spontaneous breaking of the discrete symmetry, you have a different domains. But after you take into account of the QCD effects, and then you will generate a bias. Since different domains, they will have a different potential energy after you take a QCD effect into consideration. So now, for example, you can think about like suppose we have a theta 0 equal to 0, so which is the bare one, which does not couple to the discrete symmetry order parameter, call it S, right? So here we have, you can think about S is some complex scalar, and there is a different wave, and in general there is some labeling of J to denote different domains, and for the potential of V as a function of S, so that means different n domains, they have a degenerate potential, but they also, because it's anomalous, so that means effectively they couple to the GG tilde. And we assume like theta 0 equal to 0, so there is no other part of the theta theta angle. That can be implemented using like Lewis and bar mechanism, which I will have one slide to demonstrate that can happen. And but before we talk about that, suppose you do have a theta 0 equal to 0, so now you have a different theta j for different domains provided by this scalar field. And if you have satisfied some like a greatest common divisor to be 1, then the QCD instanton will effectively break the Zn symmetry. So that means that you could have the following situation, which is if after you take the QCD instanton effect into consideration, then you will have the effective another QCD generated effective potential for different domains, and you have this kind of a, if we trust the chiral Lagrange, which is not a 100% trustable when you get a large theta angle, but just get an idea. And then you will have this could be square root of 1 minus sin squared and pi j. So different domains, like what I'm provided this example. Suppose it's Z6. You have j from 0 to 5. If you after you include the QCD effect into consideration, then you will have the j equal to 0, which is the effective theta angle equal to 0 to be the lowest potential, and the other higher j, for example, will have a higher effective potential. So now you can see that they are not 100% degenerate. So therefore, you can anticipate those some higher j domains, they will be metastable. So they will eventually will collapse and become the j equal to 0 like state, for example. And here, just to give you an idea, and the potential, sometimes we can call it a bias, potential bias, which is the j equal to 3, the maximum, minus the minimum. That will be totally determined by QCD scale. So if we do trust the chiral Lagrangian estimation, basically you can get a more precise value for that, but we should not trust that. So you get this bias potential to be like 100 MeV to the 4th power. And okay, so so I can skip this Liouville model. So you could identify there is some kind of Liouville model, which is a spontaneous CP violation model to address the strong CP problem. So what I'm trying to provide here is like we to have some possible model which is to justify our choice of theta 0 equal to 0, and by imposing the CP symmetry. And after some discrete symmetry, which is responsible for the Liouville mechanism, after spontaneous break of those Z2 symmetry, you depends on which domain of those Z2 symmetry, you could have the argument of the determinant of the R-type quark mass to be 0 or pi. So therefore, you could generate a kind of like a Z2 domains with this Z2 couples to QCD anomaly. Okay, so let me skip that Liouville mechanism. Just talk about a little bit after this setup. Then what will be the early universe story? So now let's see what we have, right? The minimal assumption we have is some discrete symmetry. Let's see Z2 symmetry, for example, which is anomalous under QCD. And that Z2 symmetry is spontaneously broken in the early universe. So that means that we anticipate in the early universe there is some formation of those domain walls. And some domain wall with theta equal to 0, some domain wall with theta equal to pi. And when you get into the QCD phase transition, then the QCD instanton effects starts to bias those two different domains. And then the domain wall will shrink. For example, the theta equals to pi domains start to shrink, and those wall will move to move closer to each other, and eventually they will try to collapse, right? And, so that's kind of the general simple dynamics. And to follow that dynamics, for example, we can also calculate more precisely what is the history points for those domain walls evolve in the early universe, for example. So at high temperature, some reheating temperature, afterwards you have the formation temperature of those domain walls, and those domain walls will reach to the so-called scaling behavior solution, and after that's very quickly reached. And after that, then you take a little bit longer time, and you maybe pass the QCD phase transition first before those domain walls to annihilate, for the T annihilation. Then those walls contain some energy, they reheat the plasma a little bit, increase the temperature a little bit, so we can call it a reheating from the wall. And then later on, you reach to the BBN temperature. So that's kind of the very simple cartoon picture about how those domain walls evolve in the early universe. But this is one picture. There are also some other cases, which if you look at this corner, so there is a possibility sometimes the annihilation happens after the domain wall dominated the total energy of the universe. So you maybe have some period of time the wall is leading contribution to the total energy of the universe, which maybe at some point is troublesome because you want to make sure that those walls they eventually will annihilate. Otherwise, you will not end up with the current type of universe. Right? Okay, so that's the case 2. And but just a little bit of 2 more like a formula which we probably need, which is about the domain wall evolution. I already mentioned after formation, domain walls reach the so-called scaling regime, which is order 1 number of walls per hep-ph. And the wall energy density scale as 1 over L. You can think about L is like roughly speaking like a Hubble size, and the Hubble size is like a T, and so such that the energy density of the wall scale as 1 over time, and the radiation energy is like a 1 over time square. So you can see that as the universe evolves, at some point the wall may be becoming important and than the radiation energy. So we can use that equality, the wall energy density compared to like a radiation energy, to define this kind of wall dominant temperature. So for some generic like a wall tension, like 10 to 16 GeV, you will have that wall domination temperature to be around 45 MeV, for example. So that means you make a higher symmetry breaking scale, you will have larger tension for the wall, then you will have a higher temperature for the wall to dominate the universe. There is another temperature, as what we mentioned, which is annihilation temperature. The annihilation temperature is roughly speaking a balance, because like what we said, right? So at some point, QCD instanton play a role to balance, to provide a bias from one domain to another domain. So therefore, you will have like a little bit of potential pressure acting on the wall. That potential pressure, if you equals to the tension pressure of the wall, and you equal that, then that will give you, roughly speaking, the estimation of the annihilation temperature. The annihilation temperature, again, because for this QCD collapsed domain wall, the potential bias is 100 MeV to the 4th power. That's determined by QCD scale. Again, you only have one parameter, which is the tension of the wall, to determine the annihilation temperature. So, and if you go to higher tension value, then you even lower the annihilation temperature. So and also in the literature, there are also some people doing more numeric estimation about this evolution of the domain walls. Okay, so that means in general, you could have a few situations. So which I'm plotting here depends on one parameter, which is the tension of the wall, which is F, a symmetry breaking scale to cubic power. You'll have some situation, for example, even in case 1, which is radiation dominance case. Suppose we forget about this domain wall dominance, which is a little bit challenging to be phenomenologically viable. Then you still have 2 situations. Either you can have the annihilation temperature of the wall disappear temperature to be below the QCD phase transition temperature. If you think about it, if that happened, then that means during the QCD phase transition, you will have some domains of the to have maybe non-trivial QCD, like first order phase transition, for example, right? So that would be the good thing for what we were talking about before. But you could also have another situation, which is maybe the QCD phase transition happens after the domain was collapsed. Then you don't have an interesting modification for the QCD phase transition because the domain was already disappear. You end up with a common theta equals to 0 situation. So you may not have interesting. What I'm plotting here about this red color, which is the so-called PTA, data preferred. PTA stands for parser timing array. Here, I just draw your attention, like it's kind of interesting that the recent parser timing array data, if we use this kind of QCD domain or collapse as an explanation, it states something on the boundary, maybe or maybe not, to have the annihilation temperature to be below or above the QCD phase transition. Okay, so let me just very briefly talk about this kind of a parser timing array data. And so that generates a lot of interest in the recent month, which is the millisecond pulsars, which is the very, very good clock, and because of their behavior, and in terms of the periodicity is very, very stable. And you can see that a variation of the frequency is very, very tiny and take a long time to them to change. And historically, people proposed to use this to detect ultra long gravitational wave. And that has been done recently and by nanograv collaboration. And they also checked this is so-called Fehling-Stern curve to make sure that the generate a signature for two different pulsars. So they are kind of correlated, but they're also correlated in certain angular distribution way, agree with the gravitation wave, which is a spin 2 object, right? A spin 2 mediated wave. If you use a domain wall to explain this gravitational wave, and we can go through some calculation. Let me skip that, and which is a very standard calculation, use Einstein's quadruple formula. But generically, you will have the amplitude of the gravitational wave, which is omega h squared, related to the tension of the wall, because the annihilation temperature, like what we emphasized before, is related to the tension as well as the QCD scale, right? So there is not much, only one parameter in this model. And there are also some peak of the frequency for the gravitational wave generated by those domain wall collapse with a given formula by this. And also some spectrum, people trying to estimate that. Let me don't get into scale, but below the peak is f cubic related to causality requirement, and higher peak, there are also some uncertainty. People find a different, a little bit model dependent behavior. But roughly speaking, because the current nanograv data is not that, when you go to higher frequencies, the error bar is large. This is so-called violin plot, which just tell you the bigger one, tell you that a little bit larger uncertainty to have the amplitude to be a certain value at a certain frequency. The nanograv, they also did use their domain wall interpretation for the PTA data, and they did find that suppose this is a contour for those domain wall explanation for parser timing array. And in general, you have two parameters to explain that, and they call it alpha. They call it annihilation temperature. Alpha is related to the wall density, energy density divided by the summation with the radiation energy. And for the model considered here, the QCD-collapsed domain wall, we only have one parameter, which is the tension. That's the tension of the, but the other parameter, which is just the choice of the discrete symmetry, n=2 or n=6. As you can see that this one parameter model potentially can be explained, can cross the kind of 1 sigma contour of the PTA preferred value, and which kind of provide a little bit non-trivial chance if the PTA data requires some BSM fix to explain. And obviously, there are some other alternative astrophysics explanation for PTA, which is a supermassive black hole binary explanation. Right? And if you take this as the one kind of constraint or data to fit, then you will have the symmetry breaking scale to be like 100 TeV or 10 to 16 GeV, which is roughly speaking the older benchmark value I was using. And another thing I want to point out is this green band. The green band is roughly speaking like 140 MeV or 160 MeV, which is the QCD phase transition temperature. And you can see that you could have some parameter value. You could have the annihilation temperature of the domain walls to be below the green band. Obviously, something will be above the green band. And such that for those parameter, then you potentially have the domain, those different domains still surviving while the QCD has a phase transition, for example. So therefore, you could have a chance to have the QCD to be first order in some domains with theta equal to pi, for example, closer to pi. If you buy this argument, we found that like, oh, this maybe provide some kind of interesting gravitational wave spectroscopy, because if we are really lucky enough, which probably maybe small probability, the gravitational wave by nanograv is explained by the domain wall collapsing, then we maybe have some explanation like that for different models and different Z2, Z4, Z6, for example. And then if some cases you will have a QCD first order phase transition, then you maybe in the meanwhile predict some frequency of gravitational wave at a higher frequency, for example. And if you're at the same time happen to have the Zn discrete symmetry breaking is also first order, you maybe even have an even higher frequency. So anyway, that's just some possibility, which I think it's worth to point out. But let me conclude. As you can see that even though the title of this talk is like a QCD-collapsed domain-worse, but I think in my opinion, the motivation I found is a little bit more important for why we are thinking about the relation between dark matter and the QCD. So in some sense, the dark matter coincidence problem really suggests like maybe there is some non-trivial relation between dark matter and QCD. And here, in my opinion, that maybe dark nugget is again could be still compelling dark matter candidate. Maybe we just need some kind of economical ways to modify the beyond standard model physics, and trying to maybe make a QCD slightly a little bit more interesting, and then that quark nuggets can be formed. And here we just provide, in my opinion, some simple situation which if you have some domain wall, those related to discrete symmetries or anomalous, that maybe can probably play a role to form those quark nuggets, for example, even though there are still some details can be worked out about the properties of those quark nuggets in this scenario. But as a byproduct, we found like, maybe the reason of the Pisa-timing array maybe can be explained by some symmetry breaking scale. But that's a little bit secondary thing I want to emphasize here. I think probably the one take-home message from my current research interest is trying to think about the dark matter is not dark, but rare. In a sense, the dark matter maybe can be explained by some standard model constituents existing particles, elementary particles in the standard model, but we just need to find a way to form those non-trivial, maybe microscopic objects. And quark nuggets, for example, is one possibility. And if that can happen, then the dark matter, maybe they do have some similar interactions as a neutron and a proton, except that because they are too heavy, right? We were somewhere like 10 to 14 grams. So they don't encounter with us that frequently, such that we need different ways to search for dark matter. Okay, so let me stop here. Thank you.
Thank you very much for the nice talk. Now it's time for questions. Any questions?
Maybe I missed it in your explanation, but how do you explain the 5-to-1 coincidence with the dark nugget model?
Simple answer is to be worked out. And there are two possibilities. There is one thing which is still probably working in the progress, is maybe there is no initial baryon symmetry. In a sense, the baryon symmetry is generated when you try to form those quark nuggets. So in a sense, you are form both quark nuggets and also anti-quark nuggets, such that there is some preference. Obviously, you also need a CP violation, and you need out of equilibrium, but you may not need a baryon number violation as one less condition compared to Sakharov's condition. And during that formation of the quark nugget and the anti-quark nugget, you have a little preference, for example, to form a little bit more anti-quark nugget. And because the total baryon number is conserving, as a result, you will have a little bit more free baryon, normal baryon states in the universe. So that one is still the work in progress, trying to think about how to work on that. But let me talk about another possibility. Suppose I don't care explain the baryon number of symmetry. I say that for some reason, before like reach to QCD, even before electron wake, for example, we do have some later baryon symmetry, right? So it's become what is the preferred baryons inside of the free neutron and proton state and the quark nugget state. So for that, and even in earlier time in Wheaton's paper, for example, he did assume, suppose you use some kind of thermal equilibrium condition that could relate the number density for the quark nugget versus the neutron and proton number density. So that will depend on the relative binding energy of the gained binding energy in the quark ligate. And because as we were arguing, right, the mass per baryon is smaller in the quark ligate state. So that means that effectively you are kind of using the similar thing like a nuclear synthesis way to calculate the abundance of the quark ligate. So indeed there is some parameter regime you maybe can explain that a factor of 5. But it's not in the how do I say, in the robust way because uncertainty is very large and people don't fully understand the dynamics and also especially the later evolution of the quark ligates. But there is some possibility, and that's probably the answer I can provide at this moment. And, yeah.
Another question I have actually is, so the quark nugget is made of the 3 light quarks, right? Including the strange quark?
Yes.
Is it supposed to be electrically neutral, or it doesn't matter if it has a large charge?
Very good. So if we ignore strange quark mass, then UDS, that's electric neutral, right? You can think about that. Locally, that will be electric charge neutral, okay? But however, strange quark does has a little bit different mass compared to up quark and down quark. If you take that into consideration, then you also need to put an electron inside the quark ligates to neutralize the electric charge. But the electron fraction will be small because the strange quark mass is not that large. And this raises to another interesting thing we are trying to calculate, which is the following point. So we are trying to calculate the electric charge distribution of the quark ligates, especially in that linear sigma model way to model the surface, because inside you have to neutralize the electric charge. Otherwise, you have too large repulsive energy, right, from the same sign charge. So, but on the boundary, some electron, suppose you use electron to neutralize the electric charge, at the boundary, some electron will be outside. It's similar like our nucleus, right? So electron is outside of the nucleus. But if you make our nucleus very large, and some electron will get inside of the nucleus. So you can easily check when you get atomic Z number to be large enough, then some electron will get inside of the nucleus. Similar like that. So we are trying to calculate the boundary property of the quark ligates. The reason we are trying to perform that calculation is we are thinking the neutron star merge potentially could be another source to produce quark ligates instead of the Earth universe. And during the merge of the neutron stars, if they are indeed produce quark ligates, and if we can understand the electromagnetic properties of the quark ligates, maybe we can check some signatures like light waves, light curvatures, for example. Maybe there are some kind of spectral lines which are from quark ligates. Maybe that we can detect that directly from neutron star merge. So that's another kind of related to your question where we're trying to perform some more detailed calculation. Yeah.
Other question?
So if you play,
Yes.
I mean, this is a random question. So if you play with some dark QCD, then you can also have a first order phase transition, and you can have some similar quark nuggets, but where you have more freedom. Does it help?
Oh, we work out this with students like 5 years ago, which we call it dark quark nuggets, and it does help. And but let me say the drawback. And the drawback is first you have ad hoc. I don't say ad hoc, right? You had some random use factor, right? Dark QCD, degrees of freedom. Another thing is like even you form those dark quark lights is a little bit how do I say, phenomenologically challenging situation, because you don't know how they interact with our standard sector, right? You see what I mean? You need to add some additional interactions when the so then you kind of don't anticipate those explanations necessarily be detectable You see what I mean? Like, you
Okay.
could be, you form some objects that they only gravitation couples to our sector, right? Then you are basically like only searching for those kind of microlength thing. Yeah, but microlength has a certain limitation, and below like some 10 to 15 gram, 17 gram. Below that, you don't see that those objects. So yeah, indeed. So but phenomenologically, I found like it's a little bit tough for that situation. Yeah.
Another question is, when you play with the theta angle, I think there is no action, but any chance to include
yes,
action?
yes. I think there is one action. So let me see. Sorry, this is not so much. Yeah, this is action.
The action.
Oh, no axion. Sorry, I heard action. Sorry, no axion. There is no axion because we imagine, even though there is a complex scalar, right? The U1 symmetry, the continuous symmetry is never a good symmetry. So you directly break the continuous symmetry to Zn discrete symmetry. And also you have Zn discrete symmetry to be spontaneously broken, right? So in sense, you don't have that light degrees of freedom in the low energy. And, so you don't have the axiom, and well, you can consider axiom, but that's yeah, it's different thing.
Okay.
Maybe you already mentioned, but how we can see the quark nugget? Is there any promising observation experiments or something?
Yes, very good. So so obviously depending on its mass, right? So here is just some naive, very naive estimation, just give us some idea. So one possibility is because it's so heavy, if it's very heavy, then the flux is so small because we're supposed they account for some 100% of dark matter. Then the flux is so small, so then you probably need like a Earth, like a big detector to potentially. If I think we estimate if you have like a gram, then maybe we need to use like a kilometer square detector and to detect that. But if you have 10 to 14 grams, so you probably need an astrophysical object to detect that. Right? But this is not totally determined. When I was mentioning a neutron star, right? Suppose you don't care about this quark nugget to explain 100% of dark matter. Suppose for some reason the quark, the neutron star merge can also produce some quark nuggets. And then earlier calculation, people estimate what is the main preferred quark nugget barrier number or the atomic charge number or Z, right? And so they basically, you can to some extent search for heavy elements way. So you can search for some object which is Z over A ratio. And normally we have the normal element, heavy element to be Z over A to be order 1, right? Like what we discussed. And you have this object. So quark nugget is the object we talk about the electric charge neutralization. And then you maybe have Z over A to be tiny. And then you may be trying to search for some exotic element. And I remember when I was a graduate student, we do have some high energy experimentalist. There is one experimentalist. His name is Jack Sandweiss, and he has already passed away a few years ago. He was just to give an idea, a sense of how exotic of the method to search for this type of objects. So he managed to get a tiny rock from the moon landing, and then he tried to check the whether that rock contains any exotic element by doing some kind of accelerator dependent mass spectroscopy for that element. He didn't find, and that also set a little bit of constraint for some lighter, extremely light actually, like a 10 GeV-ish quark nugget mass constraint. But I think in general, I anticipate the quark nugget much heavier, and then you maybe need to think about the other way. The other way would be like people also talk about like the Earth seismological activity. When this penetrate Earth, because its energy density is so high, like nuclear energy density, it will potentially penetrate Earth, for example. But sometimes it penetrates Earth, maybe it can generate a seismic activity. But this kind of a seismic activity could be also different from the ordinary seismic activity. And so ordinary seismic activity is coming from a single point. So it's more like a spherical point like earthquake. But this maybe generated some kind of line like earthquake. So you maybe can check that. So just give you a sense, like people talk about those very exotic ways to search for this type of objects. There is no universal way. And as you can imagine, like this type of thing, which also kind of on my thinking to how to detect those type of objects. Yeah, maybe there are some new ideas we can think about. Yeah.
I have one more question. Can you adjust your parameter to get the gravitational wave peak at the LIGO, the frequency range or something?
I think that's probably challenging. Yeah, the LIGO first, the amplitude is small and which is about here. So the so probably when it's this kind of 100 TeV or even the QCD phase transition, I think it's different from LIGO region. It's more like a LISA region, like a future gravitational wave experiment. And yeah. So maybe this 100 TeV has a chance, but again, the LIGO is not that sensitive. Probably you need some future like Einstein telescope or BBO to cover that. Yeah.
Any other question? Okay, I see no more question. Let's thank speaker again. Thank you very much.
Thank you for your listening.
Thanks.